Hello everyone and welcome back to another YouTube video showcasing the PicoCTF 2022 Capture the Flag. And in this video we're diving into something new in the binary exploitation category, finally diving into a buffer overflow. Let's get after it. All right, I'm gonna hop over to my computer screen. I have Sublime Text open as I need it, a Kali Linux terminal open inside of my Kali Linux virtual machine. But let's get to the challenge. This is in the binary exploitation category, and this might be the first challenge that we're starting to work on that has less than 1,000 solves at the time of recording. So maybe we are in for a doozy here. I guess I'm not quite sure yet. Again, I'm still going in cold on all of these challenges so far. Let's see. This is buffer-overflow1. Our description is control the return address. And it's also the first time we have a challenge instance or container, it looks like, that is launched on demand. If we want to go ahead and click that launch instance button, it will go ahead and start this thing up. And I don't know how long this might take, but all right, looks like it's coming through. We have apparently 30 minutes to solve this, so goodness, I guess we should get moving. It says, now we're cooking. You can overflow the buffer and return to the flag function in this program. You can view the source code here, and you can connect to the remote service using this netcat command. All right, so we have a couple things to download. Let's go ahead and play with this locally and see what we can do here. I'm going to move into the binary exploitation folder for us. We'll make a directory for buffer-overflow1 in this case. We'll hit enter, wget this down, and we have a vulnerable application. Oh, where am I? Did I not even move into the buffer-overflow1? I did not. All right. So let's move our vuln program into that and copy or cd into that directory. I wanted to make sure I went into buffer-overflow1 rather than buffer-overflow0, and there we go. Now we have a 32-bit Linux executable link format or binary file. With that said, we could also download the source code. So let's go ahead and grab that. We'll wget that down. And that is just a simple C source code file. But before we get cruising, let's make sure we remember to mark our vulnerable program executable so I could / and run it. It says, please enter your string. I will, of course, say, please subscribe. And it says, okay, time to return. Fingers crossed. We are jumping to this hex address. Okay. So let's open up vuln.c and get an understanding of how this actual program will run. Looks like we include what was an Asm H header file. You can tell by the quotes here that would have been present on the original compiler, like on the computer that was originally going to compile this code. All these others with the greater than or less than symbols, those would have been standard libraries, things that would just kind of come shipped with C and its linker and compiler and all that. We end up defining some constants, a buffer size and a flag size, given that's 64 characters in length, and a win function, being defined here as void, so it will not return anything, but it creates a character array, the buffer, the size of flag size being 64, opening up the flag.txt file, and then trying to read it if it's actually opened up. If it isn't opened up, if that file pointer or that handle isn't returned, if it's just null, then it tells you, hey, you need to go ahead and create the flag.txt file, your own local copy if you wanted to debug and test this on your own machine. Otherwise, it'll read in the contents into the buffer and then print that out on the screen. We have the vulnerable function, which uses gets, which, as you might remember from our previous buffer overflow video, is a very, very dangerous function, and it does not check for the bounds, where it might end up being clobbering some other data that could be present on the stack. Now, I've showcased buffer overflows in a lot of different videos. I'll try and cover what I can here, but ultimately this is kind of going to be the lather, rinse, and repeat functionality of determining where and how can we overflow a buffer and cruise our way up to the return value that is stored on the stack, right, above a function stack frame, or on a part of a function stack frame as it's running inside of the program in memory. So anyway, we end up reading in our own input based off of a buffer size of buff size, which is only 32. We know that we could overflow that, hence the dangerous function that is gets, and then it will tell us, oh, what even is the address that we might be going to. And get return address, I'm going to assume, is a function that would have been included inside of that Asm H header file. We can't see that in this function. in this source code, in this file itself, but truthfully, it would have been present in that we don't have access to. Anyway, the main function is pretty simple. All it does is sets up the boilerplate main functionality for a regular C program, sets out, is that a virtual buffer, VBuffer? Something that we can end up staging, getting actual output inside of a socket or a remote service like we might access this with Netcat. Just kind of boilerplate, setting effective group IDs so that we would probably be able to read the flag on the remote server, an actual game server. Anyway, it ultimately just says, hey, please enter your string, put out onto the standard output, and then we run the vulnerable function that will retrieve this. Because we are running the vulnerable function under and in through main, we could actually break and overflow the vuln function's return address. Yeah. Does that make any sense? Let me make that a little bit more visual for you if I can. Can I Google what a stack frame diagram looks like? Are there any good pictures of this thing? It's always super hard to find one. Here they're showcasing it on 64-bit. We're going to be using 32-bit, but this might be a good way to represent it. And here, Wikipedia is actually to our rescue, talking about the calling conventions or the call stack in a stack data structure used in regular computer programs and in C language and this binary that we're getting into specifically. Where is that picture? I want to help visualize this. Here it is. Okay. So, hear me out. We'll get super close. There's this thing called the stack, and it is a representation of memory and of what your computer is going to be juggling and carrying data as it is working through executing a program, letting an application run and do its thing. Now, you know, as we've been exploring lots of source code, and that you define lots of different procedures or subroutines for your code and your program to perform. Those are those functions, right? Your program can execute functions, and you've defined those with the def function. We've seen them in Python specifically. We've seen them in Java with void, static, public, etc. We've seen them in C, of course, with everything that we just read through in the source code. Now, whenever your computer moves into running a function within a program, it creates a stack frame. And that, okay, we have an encapsulated box or a picture frame, really, that is how it might reference data and information used throughout that stack frame, throughout that function. And there are a couple interesting tidbits in here. Let me show you that, right? So, in this example, let's say we were executing a function called drawLine. And while the stack frame is kind of put together in this building block diagram, there are a couple different things that are pointing towards what it might look like and what it might be doing on and in that stack frame. I don't know why it just detected in a USB drive, whatever. With the stack pointer, right? Something just kind of pointing at, hey, where are things currently on the stack? Could it be able to reference and determine what data is going to end up being used? What's going on? What data is being used for a function? All right, maybe this is going to be a problem. I'm just going to have to let that go to that virtual machine if it's going to keep interrupting me like that. You could use that stack frame base pointer to refer to local variables that are going to be used within the draw square function, or even the parameters that were passed to that draw square or draw line function that would have been used. Alongside that, as part of the stack frame, it also keeps track of the return address. Now, the return address is how your program knows that it can go back to where it was in the regular program execution after that function is complete. That makes sense, right? In our procedural code, when we would define functions over here and we called them in another function, sure, we'd momentarily go run that function and then go back to where we were executing the previous code. The way that it keeps track of that is by storing the memory address of the location to go back to on the stack or inside that stack frame box. Now, interesting thing, though, is that the variables that might be used inside of this stack frame and inside of the function, right, are bound to the size constraints that are allocated for them. You know that, and that, oh, we've defined a 32 character long buffer or a 64 character long buffer. However, with a function like gets, as you saw earlier, you could very well keep putting data inside of that buffer, and if it's not checking those bounds, the upper and lower limits, right, especially the upper limit, you could break through that and start to overflow data on the stack, in which case it'll actually pour over and clobber sensitive information like other variables or the return address. Now, the return address is something that's very, very interesting because once your function is done running and it wants to bounce back and go follow that return address, it's moving the instruction pointer to go tell the program, hey, go back to what you were doing earlier. But if you could control that, you can control what code the program runs next. In other words, you can control the program. And that is how you can perform that binary exploitation and really make it, hey, run shellcode or do something like cat a flag or open up a socket or a port to be able to get new connections in and out or disable antivirus or do whatever shenanigans you might want. It's a little bit harder in more modern security stacks, right? A lot of modern mitigations don't normally allow a lot of this sort of behavior. Trying to clobber the return address is something that could be caught by something like stack canaries. Trying to execute shellcode off of the stack isn't allowed with things like DEP, the data execution prevention, or NX, the non-executable set or bit being set for memory. And I know that's a lot of words, and I'm super duper sorry for rambling for so long, but I hope that gives you, for one thing, a little bit of a better visual. And the idea that what a buffer overflow really is it's, hey, pouring water into a cup, so much so that you have so much water that the lid or the cover overflows and pops off. And now you might be able to do more damage with, hey, what liquid, what beverage was originally inside of that cup? You know? Super weird analogy, I don't know. But I hope that helps you define it and visualize it in a way. The stack is something that you are taking advantage of for a stack-based buffer overflow when you're clobbering that return address by overflowing data and reaching up to break it. Now, going back to our specific example in the program here, how could we control the program by modifying the return address and go to this specific function when that would tell us the flag? Otherwise, that's never actually ran by our program naturally, but it exists within the binary. It exists in the program. It's something that could be executed if we could control this instruction pointer. So let's figure out what we could do by experimenting with that. We know, okay, we could send data to our vulnerable function by supplying it as a string. We knew that, hey, okay, it would take 32 characters of input, but could we give it more than that? Could we break through that? Let me end up creating probably just some simple Python code, and I'll make another terminal over here on the side where I could take the letter A, sure, but multiply it out 32 times, and now I know, okay, that specific length might make the program do something strange. Let me enter that. No, I'm not doing anything different because we're at the limit. We're at the end of it. That buffer allocated for our input. But say that is something that's going to be the very, very first variable defined inside of this vulnerable function. Now, if we were to keep climbing and if we push more data onto the stack or get more data input, all of these things in a 32-bit architecture, which is the architecture of the program that we're working with, those are all values and information and data stored in sets of 4 bytes or a D-word value. And what I mean by that is like, hey, you might have seen hexadecimal stuff like 0x dead beef, just an example. 0x representing this is in hex. But all that really is a couple bytes being represented in different ways. We just took 4 bytes, and 1 byte being one specific set of 2 letters or 2 characters, and cramming it all together to be 4 bytes. D, E, A, D, B, E, E, F. So if we knew on the stack above our specific variable, like our buffer was there, what is going to be 4 just beyond that? If I were to multiply 32 times A, or A times 32, but also add 4 to that, so I'm really multiplying it to 36, does that give me anything different? Let's try it. Not yet. Okay. Did I clobber anything there? Or were there bounds in the way? It's worth experimenting with. Let's try and crank it up even more. Let's add another set of 4 in there, so we're going to now 40 as the length of our A values to try and spam this thing. Make it choke. Give it too much data that it overflows. So that causes a segmentation fault, you might notice. And it's an interesting thing. Did we break it some way, somehow? If you can, you could use a program like dmessage within your computer or within your Linux virtual machine or operating system in Linux that you might be running. And you'll need to use sudo permissions to be able to actually read this data out. But at the very, very bottom here, you'll notice there's an error message that we got a seg fault or a segmentation fault. That means the program did crash. It died, it broke, it choked, and it actually has 0 for the current instruction pointer. Kind of odd, kind of interesting, right? Why would that be? Well, keep in mind, hey, we actually had a big long string, but it is a C-style string, as it's a low-level string stored within memory. So the way that programming language C in the low-level memory stuff will denote the end of a string variable is it will add a null byte character to it. And that null byte is the 0x00, sometimes represented in the \x representation of 00. Actually, might just be /0 in some renditions. You might see it in different code and scripting language or programming languages. Sorry. So 0, of course, if it were to be interpreted as the null byte, if it were to be interpreted as a number or like an address, it's still just 0, right? So could we then know, okay, we have filled up to the point where just the trailing and ending null byte is getting pushed into that return address or instruction pointer placeholder. Let's try and see what we might do if we gave it another 4 bytes or another D word value. I know I'm adding, 4 in here. I'm just trying to find that sweet spot where we might be able to make this program crash. Let's use tacvuln again, supply our input string, and it's jumping to something weird or different this time. We also see our segmentation fault. Let's check dmessage one more time, and now that's put me at a weird spot. Did I do something wrong? I'm not quite sure. Let's keep experimenting. Let's add another 4 and see if we can get anything that's more reliable here. I'll use vuln. Slap in 4 of them. Ooh. You see something there? Our jump address return value changed into something completely different from the values that we were receiving previously. Previously, it was just like 0x8049324 blah blah blah. But now it jumped to 41414141, which some of you smart people might notice and recognize is actually the hexadecimal value for the A character. Right now, Python is going to return the ordinal value of this A character in its ASCII representation. But if we were to take the hex value of that, because that is just in decimal, right? Python's going to want to tell us to it in base 10, but our computers and the bytes are storing that in base 16, hex 41. So we just saw ourselves clobber that instruction pointer, that return address. So we really we clobbered the return address, and now we can control the instruction pointer, and we can make it jump to any address that we might like. Let me show you that one more time, and let's get the dmessage value in there. I'll grab this big long payload, slap it in, and let's check out sudo dmessage. Nice. See how this has a segfault at 41414141 as the instruction pointer, as IP? That means we can control where our program is going to go next. Now, where do we go? Right? We know we want to call the win function, but where is that within our binary? It is something that has been compiled into the binary, and it's part of it. So maybe we could determine where it is by using some other neat tools. There's a really good tool you could use called readelf. Should be something kind of known on Linux and common and built in. You could pass in the file or the elf binary that you want to get some information on. Now, if I hit enter on this, it kind of wants to know, okay, what are you going to do with this? What other options might you want to retrieve out of this? You could use like, hey, tell me everything that you know, or I just want to see the file headers, the program headers, section headers, etc., etc. Something really good to look at are the symbols, because if the binary isn't stripped, as in, hey, the symbols were removed at compile time, this one is not stripped. So just for our sake of learning, for our education's sake, we could actually tell where are what functions in the binary. Let me show you that. Let's use readelf tac s to retrieve those symbols from vuln. And now there's a lot here. I know this is kind of dumped out, but you could see some things in all over the place between different sections, between different objects that it saw, or files that it might have loaded as needed. You also might notice some of these func things. This is the column that I'm looking at. Very, very sorry. Should have been more explicit about that. But notice you could see there is our func for the vuln function. You also might be able to scroll down and find, ooh, I see the func address for the win function. And over on the left-hand side, it tells us, it shows us what the hexadecimal address for that function call is. Kind of cool, right? So we could actually use that. We know, okay, that's where we're going to end up passing this and telling the program to go next. But let me show you something. I know it's kind of odd. We were using this vuln thing and adding in what was, hey, A's, and actually the last four were what we knew were a instruction pointer clobbering, right? So let me grab BBB here, and I'll actually just note this as a comment so I don't still have it in my clipboard. I'm using BBB as the example. Hey, this is where we control the instruction pointer by clobbering the return address. But if we tried to add in 08049, etc., etc., it's not just going to be tacked on as a string, right? Because this is obviously longer than 4 bytes in this case. That's like a hex address on its own. Trying to jump to that isn't going to give us the right thing. See what I mean? The way that this is put together is that it is real legitimate bytes. And those bytes, as I mentioned to you, well, sure, we noted them with 0x to prefix this is in hexadecimal, but that's stored within memory in a super special way. It takes the \x representation when we want to refer to these as real bytes, but it also flips them in a weird way, and that's called little endian encoding. And it actually kind of takes and rearranges all of these. And I'll show you that to you in a backwards way. Say we had this right here, but we wanted to start from the end, working at a byte at a time, and have it flipped backwards. Saying that out loud, I know makes no sense. But what if I said this is going to be the same as F1, or F6, grabbing this byte, and then 9.1 grabbing this byte, 0.4 that byte, 0.8 that byte. Whack, right? Now, obviously, as a hexadecimal value, that's wrong, but denoting each of them as their own byte, that is the way to properly represent that. Because little endian encoding takes, the last couple bytes and flip-flops them. Let me show you that. Let's try and copy this in. And bear in mind that \x is, again, just a kind of prefix formatter to tell something like Python, hey, I want to represent this as a byte value. I'll include that in as a string here, pasting that in, but we see we have some weird character here. We could like copy and paste this, and we could try and run this in the program itself, but the \x's are still going to be interpreted as if they were literally a \x and not how we want the bytes to be represented. So we kind of have to rely on Python to actually print this out for us. I'll use Python -c. How about that? So I could actually use like a command all within one line without ever actually opening up the Python interpreter itself. It just executed it and brought me back to my regular bash prompt. So let's actually go ahead and actually use our Python 3, but we'll have to do something weird and wacky. Because if I wanted to print out all of these values, does it keep these here? Are those actually displayed? I'm not quite sure. Let's try and pass that to XXD so we could see the hexadecimal representation of it. And ooh, I do see it here. You'll notice our 910408. We also had a C2 in here though. So was there some oddity? That byte might have been represented like a Unicode character or something strange. So maybe it's probably best to represent that as still how we saw our \x to begin with. That was what, F6? Yeah? Let's print that out to the screen. So that will display it, but reading the bytes with XXD, having that just displayed out in its hexadecimal output, is it doing anything weird there? I'm not quite sure. You know what? Let's try and kick it over to the program. I'll use pipe2./vuln, and that still breaks because our bytes are wrong. So let me tell you, our print function isn't exactly our friend anymore because it's trying to play nicely with those things that could be represented in another way, like maybe potential Unicode bytes, or stuff like that. They have a different sort of character set encoding, voodoo magic, witchcraft that we don't need to really dive in the weeds on, but we know that we can't trust our print function anymore. So let me tell you, in Python 2, that used to be just fine. But in Python 3, we have to do some other boilerplate stuff if we want to do this all in line. We would use something like the sys module. And let me add a semicolon to denote, hey, we'll use a new command here. And I'll actually use something really weird. I'll say sys.standardout.buffer.write. And that is the function that we'll call to try and display this here. Let's see, how does that come through? No, Python 3 needs everything in bytes, right? If I didn't want to print real bytes. So we'll have to prefix that with the character B right in front of the string. That's how we can tell Python 3 this is a byte string. And that'll naturally and properly interpret our \x representations. So we'll fire that up, and ooh, now we have some new output, and piping that to XXD to get that hex output. Now this looks like exactly what we wanted. F6910408, which is what that value from readelf was. While it was originally given to us in hex, we want to represent it in that little endian format. Yeah? You following? I know there are a lot of steps here, and maybe I'm not doing the best job of cutting through it, but I hope you are following just a bit. If I had this output running, and if I kicked that to our vuln program, ooh. You see that? We jumped to the correct address, and this is the output that we would have expected from within the win function, defined right here. There's that printf output. So we did it. We jumped successfully to that win function. Now we just need to have our own like flag.text. Let me go ahead and echo something. Hey, we'll put like a John flag, please subscribe. And wrap that into a flag.text. Now let's run the same payload that we had previously using Python to display these bytes and pass it to the program. And there it goes. It displays that flag for us. So that's it. That's all we needed. We needed to go ahead and carve this out and actually send this to the remote service, which we have here. And oh, we only have 35 seconds left. So let's do it super duper quick. I'll copy and paste this code. Let's get the same command we were going to run, but rather than to our local binary, we pass it to the remote service. Please enter your string. Oh, it's not going through it. It's not actually sending it. What are we doing wrong here? Do we need to echo this out or something? Pass it through with parentheses? Something was super duper wrong in that setup. Well, echo was probably going to end up displaying all that. So can we echo super quick? No, that's not figuring it out. Dang, we ran out of time. So let's take this one step further. I'll restart the instance, and rather than trying to do this through, hey, just one crammed command line, let's write a Python script to be able to actually exploit this thing and send it in a natural way. You want to do it? Let's dive in. I'll go ahead and restart the instance so we have a little bit more time. That'll probably give me a new actual host name or port, or a different port number, one way or the other. But we've sort of made sense of how this whole structure came to be, right? What if we were to write a script called exploit.py? And I'll add a shebang line, of course. It is going to be a Python script, but I'm going to import a different module. I'm going to import socket, which is the built-in Python library for allowing us to interact with like a remote socket or port out somewhere out on the interwebs. I'm actually going to go ahead and import argparse. Yeah? So that way we could tell it, hey, what host name or port do we want to use for a given command line argument? If folks aren't familiar with the syntax of argparse, that's totally okay. Let's try and crank it out together. Let's say we have a parser object or a variable that will end up retrieving the command line arguments that we want to have our program understand. We'll create an argparse argument parser object. There we go. And now our parser will take a little bit of know-how. It's going to want to have arguments added to it with an add argument function. We'll take in a host argument, yeah? And we'll supply some keyword arguments that might represent how this is going to be interpreted. Look, it's going to be a type of a string, because we know, hey, a host will just be like an IP address or a domain name. And we can say help, or like the description can be the host name or IP address to connect to. And I'll add a comma there so that Python black will clean that nice and easy for me. And we'll do the very, very same. We'll actually add another argument for the port. That, of course, will be an integer, right? Just a number representation. And then we could say the port for the service to connect to. And then once we're done with that, we'll have to go ahead and say args will equal our parser parse args. And now all the variables that we might want to refer to are represented within our args variable. Let me show you that. Let's do a, hey, print args.host or, and actually args.port. Cool. Does that make sense? We're just going to simply parse the args and then put them out on the screen. So let's run our exploit script, and we did not supply the proper arguments, so it said, hey, we actually need these. They're required. So if I were to add in, what is it? Saturn PicoCTF.net at 60940. Paste that in, 60940. There we go. Now it just printed these out nice and easy for us. But we want to use our socket to connect to it, right? So let's use a context manager, kind of the same way we've been doing with like file handles, but actually a remote socket handle. And we'll use the constructor for a socket object within the library or module that we're using. And we'll just call that with the as keyword, something like the connection, right? That will automatically close the socket for us, so we don't have to run, hey, connection.close at the very, very end. It just handles that all for us. Now we could do actually receiving data or sending data to this socket. Let me show you that. Let me do connection.recv. That could work, right? We could be able to receive and send bytes back and forth, but we need to like actually connect to the host and port first, right? So I know it sounds weird. I'm creating this connection object, but we have to actually make the connection with a connect function as a property of the socket object. That'll take in a tuple, so parentheses inside of the parentheses, and we'll give it our args.host and args.port. Yeah? Okay, let's see if that works. I'm just going to run the script super quick. No errors, so that looks good to me. And now we can go ahead and do like, oh, the connection.receive that I was referring to. I'll print that out so it's displayed here for us. But receive is an oddball in the socket library. It actually takes one argument as to the maximum number of bytes to receive. It's kind of a standard boilerplate thing, just to pass in 4096 as the argument for receive. So running that, after I save the script, it gives me the byte string. Hey, please enter your string and the new line character ready to receive data. We could decode that if we really, really wanted to. And that'll actually go ahead and remove the byte string quote surrounding it. But that's nice and dandy. We want to be able to actually add our payload and send that. Connection.send, given a payload variable we'll create. So let's actually build this payload. Let's say we had, let's keep it weird. Let's make it an empty list for this sort of thing. Yeah? Actually, let's define some things that could be present inside there. We knew that we sent a lot of A's. Yeah? We actually sent, what was it? 40? Let's go back to our notes here. Yeah, we sent 32 plus 6, which was 36. Did I say 36? 32 plus 4, which is 36. And then add 40, and then add 44, actually. Okay, and then we had our new instruction pointer value. So let's go ahead and say 44. And actually, let's keep track of that, because that's actually valuable information. Let's say that's an offset to where our instruction pointer might follow. We'll have a new instruction pointer. I'm adding an E in here to refer to the register name, extended instruction pointer. It's not super important, but we knew that our new EIP was this previous value, F6910408, as the little endian representation of the win function that we retrieved from readelf. Now, we carved that out manually, just kind of flopping the bytes around. But if you really, really wanted to, you could actually use some other kind of magic within Python and create a little endian representation based off the original hex value that you got from readelf. So you don't need to worry about figuring out, oh, the \x reversing things around. I'll show you what that is. You're using the struct module in Python, and that module will let you actually pack data and represent bytes in some way or another. You'll have to specify how you want it formatted, and this is kind of a special thing where you have to press the I believe button. It takes a specific format specifier, being less than symbol means little endian, and capital I means integer, or I think, right? We could at that point pass in 804091F2 or whatever the heck this was. That's the benefit of, hey, us using readelf tac else vuln, grabbing the win value right here that we saw previously and denoting it as hexadecimal in Python. Let me try and print this out super quick, and I'll actually have that displayed. We'll run that. There is our byte string. I know this is going to error for the moment, but we know, okay, we are properly getting the new instruction pointer or the new location that we want to go to in the binary. So we'll call this new EIP, and we'll bring that down to where we had it previously. Nice and easy. The thing is, our payload right now is a list. We want it to be a byte string. So let's actually bring it all together with the same way we used to join stuff previously, but let's add a B prefix so it can be bytes. We could do that with our payload. And in all honesty, we could probably make that cleaner by doing this join statement, like as if we were doing it for the declaration of our payload right here. I know it looks kind of messy, and that, hey, we got a little bit more indentation going on now, but that sets us up so that we have a nice structured understanding of how our payload works and maybe anything that could follow it. But ultimately, we are just overflowing to the point where A's crash through the buffer, clobber the return address, and we give it a new instruction pointer to jump to, which is the value of that win function within the vuln binary. Now, when I send this, it's just going to send it. But we didn't see any other data because we didn't receive anything else. Our socket sent it and then closed based off of our context manager. So let's try to now go ahead and receive anything that follows after we sent our payload, and let's see if it'll just spit it out for us. Not seemingly. Okay, what have I got going wrong here? Is it going to get an error somewhere? Part of me genuinely doesn't know. I'm not quite positive what I'm getting caught up on right now. I am sending our payload with the right instructions. Do I have to add a new line character at the very, very end here? That might make sense. We are, of course, hitting enter after we send it. So let's add and tack on a \n bytes to represent a new line. That's sure nice and easy to say. We hit enter on our keyboard with a netcat connection. Let's try and see what this gives us. Ooh. Okay, time to return, fingers crossed. We are jumping to the address that we expected. Let's see if the next line that follows is the flag. And it is. Addresses are easy. That is the flag. And we could actually not print out that line before it. So we have a nice and easy get flag script. That is our exploit, ladies and gentlemen. And we have completed our first buffer overflow for PicoCTF 2022. Sweet. We spent, what, 40 minutes on that thing? Hey, I hope you had some fun. I hope you learned something new. I mean, look at that. We have plenty of time left after we scripted it. Let's go ahead and paste in this flag. And that challenge is complete. 200 done. Challenge that has less than 1,000 solves, but we cruise right through it and learn some good stuff all along the way. I hope that all made sense. I hope, hey, building it out from the command line first, kind of getting the high-level theory and lecture on what the stack frame looks like, finagling and bumping around trying to find a proper offset based off of what we knew the buffer length was, and then really putting it together in a smart way in a Python script. This gives us a lot of flexibility for other opportunities in the future for buffer overflow or binary exploitation, stuff like this. And I know we are going to see some other buffer overflow challenges for PicoCTF 2022, so this is code we might have to hold on to and maybe keep for our own notes. But with all that said, everybody, I have been rambling for way too long, and I hope you did enjoy this video. I hope you learned something new, and if you haven't, maybe, hey, go explore some of the other buffer overflow videos that I've done. I have way too many on my channel, but I know it's an interesting and fascinating thing that people are interested in, and it does help. It helps you learn that grit, that tenacity, that stubbornness, and determination to get this thing right and capture that flag. Thanks so much for watching, everybody. I hope you enjoyed this video. If you did, please do all those YouTube algorithm things, like, comment, subscribe, anything to help the channel grow, share, support. I love it. Thank you, everybody. I'll see you in the next video. Take care.